virtual session. Hopefully you're here for earth science. I had a few people earlier who were in the wrong class. I do teach biochem and then earth science back to back. So if you tune in early or late, you might actually end up in a different class, just so you know. We are going to do quite a bit today. We're going to talk about virtual session expectations, some helpful info about the course, and then we're also going to review basically the three main parts of Module 5, which is absolute versus relative dating, geologic time, and the origin and evolution of life. And then we're going to complete the Module 5 DBA. So that's quite a bit of stuff. I think it'll probably take us about 35 minutes, I assume, because this module is pretty short. So virtual session expectations, right? Camera is on. You don't have to have the camera on your face the entire time, right? You can tilt your screen slightly or angle it, but I do want to be able to see at least part of you so that I know that you're actually there and you're not just logging in and then leaving. Participate, right? This session is for you. So answer questions to show me that you understand. Ask questions if you're confused about something or you need help with something. And, you know, if I say, hey, what do you guys think about this? Make sure you're responding. Be respectful, right? Of course, to your classmates, just like we would in any situation. And take notes. So last semester, I actually graded notes. This semester, I will not be grading notes in the course, right? But it's pretty hard to be successful without notes. Also, if you have notes, then you can redo quizzes, right? So if you take a quiz and you get a score that you don't want, it's too low, or you think you could have done better, you can always email me your notes and I'll give you a retake on the quiz, right? That's to show that you're actually trying to learn the material and you're not just trying to take the quiz and then retake it a million times until you get 100. So, course info. This class has a lot of assignments, right? A lot. Basically, earth science is kind of like an overview of science, right? It's going to cover things from geology, from biology, from chemistry, from general physical science, right? So there's a ton of assignments in this class. I spaced it out for about 3 a week. But if you get off pace, it's going to get really hard to catch up, right? So do the best you can to stay on pace. There is one collaboration assignment. It's going to be due on May 18th, right? So that's in a really long time, but just keep in mind that date is coming up eventually. We have a pretty large class, so we're going to try to find partners for this collab project. If you can't find a partner or you really dislike working with a partner, then you could work by yourself, right? We could talk about that. Of course, there's going to be a choice, pretty much one per every module. So we will go over that when we get closer to May. But as we go through the modules, be thinking about which modules are interesting to you. Because if you're going to do a project, you probably want to do it about a module that you understood really well and that you were interested in. We're going to do all of our DBAs during the virtual sessions. So, for example, today we're going to do Module 5 DBA. You might not be ready for it yet, but you will be ready for it after we get through this PowerPoint. And not only that, but then that way we can do everyone at once, and it saves you some time in having to try to schedule a DBA. If you're not able to make it to the virtual session, right, then email me and we can do the DBA separately, but do your best to come, especially on DBA virtual sessions. Okay, so first thing is first, geologic time, right? What a doozy of a first assignment, I will say that. It was hard, right, because you had to do math, you had to sort of create this scale, you had to look at significant events, you had to reflect on it. It was a lot to do for the first assignment, right? So I know that most people did really well or revised to include things that they left out. But really, the main point here is that not all of these time periods lasted the same amount of time, right? So geologic time is not divided up like a clock. It's not like 1 hour represents one period, etc., right? Some periods were longer than others. What do you guys think? Why do we even classify geologic time into periods? Like, what is the point of breaking it up into periods? What makes a period special? Respond in the chat, please, or you can speak if you'd like. What makes a period special in geologic time? Why do we organize by periods? Okay, Sydney says, probably, I think it's because the periods show evolution. True, right? Some of the periods are marked by animals that dominated or plants that dominated that time period, right? So if we look at this first picture here on the left, that's exactly what we're seeing. We're seeing which animals dominated during these time periods, right? Of course, the earliest really known living organisms that we have fossils of are these trilobites. I hate scientific language sometimes, which are like those horseshoe crab things, right? Have you guys ever seen a horseshoe crab? Let's look at one on Google. They are, there's some scary looking animals, not gonna lie. I went to a museum once and they had a bunch there. Trilobites, thank you. It was all blurry. I couldn't tell where the Y was. So horseshoe crab blood, that's weird. This is what they look like, right? And then this is what they look like on the underside. They have a million legs. They look very alien-y, right? In fact, they remind me of the movie Alien versus Predator kind of thing. I would definitely see one of those things launching itself at you. They don't though, right? They're not attacking anything. They're pretty much just crabs. They just chill. Autumn says that we want to know when significant events happen so that they're not all jumbled up. Yeah, right, because geologic time is spanning 4.6 billion years, excuse me. That's a really long time. We need a way to divide that up somehow, right? We can't just say, oh, well, this happened 200 million years ago. Everyone's like, what? When's that? I don't know when that is. We need ways to categorize and organize this information. So these are the current living relatives of the trilobites, right? Those were the first kind of creatures to exist, which, you know, they're pretty simple. They don't need a lot. They are like crabs. Most as an animal that you probably know about today. Then we also start going through like getting all these different animals, right? Most of these are sea creature type organisms. They're swimming, right? You can see the tails. They look kind of like squids, right? We get into like starfish looking things. Then we start getting into the dinosaurs, right? Of course, Jurassic Park was called that because it's based on the Jurassic period, right? Triassic was also a period when dinosaurs reigned. We also have the Cretaceous period, Tertiary period, etc., right? And so a lot of times these periods are categorized by which animals or plants were dominating that time period. A lot of times we also just lump some of these things together, so we might refer to anything before the Cambrian period as Precambrian. It's so old, it's before the Cambrian period. Also, this picture here, which you might have seen in Canvas if you went through this lesson, right, is showing us more about like how long each one of these time periods is, and is giving us some information about the coast ocean levels. So this blue stuff over here is actually talking about ocean level. So that's another reason that we might categorize these periods is based on geologic events. There was a huge change in the atmosphere. There was a huge change in the ocean. There was an extinction, right? There was volcanic activity, a meteor hit, right? Any kind of geologic change could signal the end of a period and the beginning of a new one. So thankfully, we don't have to memorize any of that stuff for this class, right? But it's important to kind of understand that the point of the periods really is to organize our knowledge about what's going on in the history of Earth. So the most interesting thing about this, at least to me, is these mass extinctions, right? There's 5 major mass extinctions in the history of Earth. So we're going to talk about a little bit about them. First one was the Ordovician extinction, 445 million years ago. Likely causes: rapid global cooling, falling sea levels. Why do you think we say likely? Why don't we just say cause? Yeah, it's a hypothesis, right? Was anyone alive 445 million years ago? No, no one knows if this is true, right? We're assuming. We think that those falling sea levels caused coastal areas to get destroyed. And of course, if the Earth is cooling, chemical reactions can happen, right? That's going to actually kill off a lot of stuff. So the death rate for this extinction was 85% of living things were wiped out. The Devonian mass extinction, 70% of species were wiped out 340 million years ago, most likely caused by an asteroid followed by rapid global cooling. So why would an asteroid cause global cooling? That's kind of a hard question. Why would an asteroid cause the Earth to get colder? It sent gases into the atmosphere and debris, right? Think about it. If you have a rock and you throw it into like a dusty field, right? Stuff flies up in the air, right? Now imagine that you have a rock the size of a planet that hits Earth. Lots of stuff is going to get thrown up into the air, right? It's almost like when there's volcanic eruptions with ash, that debris stays in the atmosphere and sort of prevents the sun from coming onto Earth and actually cools the Earth. So in that case, ocean life was severely affected, right? Of course, if you were near the asteroid where it hit, obviously you're going to die, right? But things not near it also died. Permian. This was the biggest and most intense mass extinction. 95% of species died. Almost everything, right? That's a huge, huge mass extinction. That was 250 million years ago. Likely causes were volcanic activity, increase in methane and carbon dioxide, and then rapid global warming. So global cooling caused the first two, right? Seems like a lot of stuff could survive the cold. Global warming, not a lot of stuff survived, right? Which is part of the reason why scientists get super annoyed and upset about global warming, right? Because global warming caused one of the biggest mass extinctions in Earth's history. So we care about that, right? We don't want that to happen again. What ends up happening when we have too much heat, right? We have an increase in carbon dioxide and methane. We have less oxygen. Remember dissolved oxygen from last semester? Oceans lost oxygen. Stuff died, right? Land started becoming desert. Plants died. And then as we know, when there's no plants, nothing else is living, right? So that was a huge one. Then we have the Triassic extinction, which of course is also a pretty big one, but not quite as big. 76% of species are killed. That was 200 million years ago. And similar situation, increase in methane and carbon dioxide, rapid global warming, desertification of the land, and heat waves, right? So again, a heat situation, not quite as severe as the Permian mass extinction, right? But again, really what's happening is when the Earth cools or heats, we see an extinction. And then the KT mass extinction, which was the most recent, and by recent, I mean 65 million years ago, not that recent, most likely caused by asteroids, volcanic activity, and falling sea levels, right? So again, what happened? Well, the volcanic activity and asteroid impact caused a ton of fires. So imagine that the Earth is on fire. Not very pleasant. Plants, of course, stop getting as much sunlight. There's ash in the air. Remember all the ash that was here in the summer? Right? And it was like falling from the sky. It was like that times a million. Plants were dying. Right? It's known as a nuclear winter, right? Where it actually basically caused some cooling of the Earth. The sea level fell, and 80% of species died, right? So you can actually go back to one of those images that we looked at for extinction, or excuse me, for geologic time, right? And we can see where those things were. So like the Triassic mass extinction was probably following the Triassic period, I'm pretty sure. So in here, right, the Denovian one in here, right? So they all happened either right after or right before a period, and that's kind of how we distinguish them. So somebody says in the chat here, Sydney says, well, Yelena says that's so sad. Yeah, it is sad, but at the same time, right, part of the concept of this is the extinction of a lot of these species actually gave rise to new species, right? So for example, rats survived a mass extinction. I mean, we believe it, right? They just survive everything. And they actually gave rise to mammals becoming a dominant organism. So if there wasn't a mass extinction, rats probably never would have had the opportunity to survive something and then grow and develop into larger organisms, right? If the dinosaurs never went extinct, we probably wouldn't exist. Can you imagine if you went outside and there were dinosaurs everywhere? Right? It would be Jurassic Park, but worse, because we wouldn't even have cities, right? Because they would destroy them. So a lot, yeah, Flintstones, I mean, I guess that would be a positive way to have dinosaurs, but still. Right? These mass extinctions actually allow for new organisms to take over on Earth. Sydney says, if you think about all this, the world naturally kills each species off so humans could get killed off at some point, and future species will study us and we will be like dinosaurs to them. Hey, that's a cool point, Sydney. And it's true, right? In fact, many scientists predict that right now we're in the process of the 6th mass extinction. A lot of species are going extinct. Partially because of humans, partially because of global warming. We know humans also contribute to global warming, but we also see that even before humans, the Earth naturally warms and cools, right? That's already happening. We might be making it worse, but that happens, right? And that's true. Will humans last forever? Probably not, right? So it's something to think about. Now, of course, we're talking about millions of years, right? So look at how much time was in between each of these mass extinction, like 100 million years-ish. So quite a bit of time, right? So when humans go extinct, right, it might be long after you're dead, but it could happen. Okay, so why do we care about geologic time? If I didn't say something there that made you care about it, well, hopefully these things will make you care. We can see the history of the change of Earth, right? How has Earth changed over time? That's important, right? Earth changes. It hasn't been the same, and it's going to continue to change. So of course that will help us make predictions. What will Earth be like in the future? Can we survive through a mass extinction? Probably, unless there's a bunch of asteroids hitting Earth, right? Who's surviving asteroids hitting Earth? I don't know, probably not a lot of things. Plants survive almost everything. We can analyze the evolution of life, right, as a response to changes on Earth. So how has life changed and adapt over time? And then, of course, we can understand that the Earth has changed over time. Some people don't understand that, right? They don't believe that. They're like, no, the Earth has always been this way. No, right? The Earth used to be super toxic. So the change over time part is really the main reason that we care about this. We want to see the change over time and how it's influenced living things, but also Earth. Okay, shifting gears here to absolute dating versus relative dating, right? This was a lesson that you should have completed. There was a quiz. So the difference is absolute dating means that we know for sure exactly how old something is. We use radioactive isotopes for this. So you might have seen on crime shows, they actually use absolute dating. So have you ever seen a crime show where they find a pile of bones somewhere? Right? And they're like, oh, whoa, when was this person killed? I don't know, right? And they do some kind of lab testing to figure it out. Well, what they're doing is absolute dating. They take a carbon isotope from the bone, right? And they actually can analyze how much that isotope has decayed over time, and they can tell you exactly when that person died. Pretty cool. So we can do the same thing with rocks, which is maybe less cool than bones, but still. We can take a rock, we can take the carbon out of it, we can see how it's decayed over time, and we can determine how many millions of years old or years old the rock is. Absolute. Think about what the word absolute means. I'm absolutely sure how old the rock is, right? You know. You can assign, I mean, not with 100% certainty that it's like, 1 year and 2 days and 4 seconds old. Okay, we're not getting that specific, but we could say it's 200 million years old, right? 250 million years old, whatever. Relative is an approximate, right? I'm relatively sure how old this rock is. I think it's this. Relative dating really is based on where the rock is found. Was the rock found deep in the earth? Was it found in a more recent layer of the earth, right? And basically we're comparing it. Oh, well, it was found next to this rock that's really old, so we're going to say it's the same. Relative dating is more for in situations where maybe there aren't any isotopes in the rock, which is pretty rare, or when it's a really heavily studied area and we kind of already know a lot about the rocks there. We could just say, oh, this rock is this old based on where it's found. So scientists use these techniques, right, to prove the age of something. Now I'm going to go into a side little rant about something cool that I got to go to one time. I went to a lecture about what killed the dinosaurs, right, with a scientist who actually his entire job was to find what killed the dinosaurs, right? Most people think it was a meteor. However, they couldn't find the crater, right? If a huge meteor hit Earth and killed all the dinosaurs, wouldn't we see a crater, right? So he, first of all, looked for that, and he also looked for an iridium layer. Iridium is an element that comes from space. So if we see an iridium deposit in rock, that means that an asteroid or meteor hit and iridium was released and layered itself in the rock. So he found both. He found an iridium layer that was in rock that he used absolute dating to find the year of, which matched when the dinosaurs went extinct. And they found the crater. It was actually right on the Yucatan Peninsula. They used gravity sensing technology. Really deep holes in the earth, right, are going to have stronger gravity because they're closer to the center of the earth. So they actually did gravity sensing and sort of went around and found that actually the meteor, I think it was, the meteor itself was like a mile wide, right? It was huge. And it hit, obviously made a humongous impact, and it goes on like the Yucatan Peninsula and into the ocean. So there is a crater there, we just can't see it because it's so old. But they were able to find it with the gravity sensing. Right, so that was kind of a combination of all this stuff so far. The dating of the rock was important to prove how old the rock was and that that iridium came from that time period. And then, of course, finding the crater, which was like a separate thing, to prove that it was a meteor that had caused that to happen. Right, so this is the kind of way that they came up with these things on the chart that we looked at with extinctions. Right, these likely causes are because either they found some kind of evidence for these things, right, or it's, they know that the earth cooled, so then they're able to predict kind of what that would mean, right? So there is evidence here. They're not taking a random guess. But again, it's almost impossible to prove 100% because there are still people who think that it wasn't a meteor. Scientists, not just people, scientists. Anyway, it was really cool. That was the coolest lecture thing that I ever went to. Okay. Absolute dating, right, is based on this concept of radioactive elements that decay over time, right? Pop a one in the chat if you've ever heard the term half-life. If you play video games, you should be putting a million ones in the chat right now, right? Half-life is a really common video game thing. So what it means is that over time, these radioactive elements decay. Thank you, Haley. Lots of enthusiasm. Yeah, in a video game, right? Well, of course, this video game concept comes from science here. So we start out with 100% of the element, right? And over time, it decays into a radioactive element. So we can measure how much of it is radioactive, and that will tell us basically how long it's been decaying. And different elements have different half-lives, right? But we know them. So for example, if we find carbon and we find out that 50% of it has decayed, right, or become radioactive, then we would know, okay, the half-life of carbon is, you know, I'm making this up, 200 years. So it's been 100 years since this carbon was in this rock. So it's basically the concept of taking this decay and using some math to figure out how old something is, right? And that's why it's absolute, because math is involved, rather than just looking and saying, well, it's probably this old. Okay, so we use that concept of a half-life and that the fact that radioactive elements decay. Okay, thankfully we don't have to know how to solve for this, but if you take advanced science classes, you will learn how to calculate this stuff. It's a formula, it's not that hard. Relative dating is more the concept of, okay, rock on the top is the youngest, rock on the bottom is the oldest. And then, of course, rocks don't form perfect layers, right? So then we might get something like H, where we have a weird rock layer, probably that was magma or is magma, that sort of transcends multiple layers, right? That happens. Regardless, if you're a scientist and you found, let's say that you found a fossil right here in the B layer, right, you would be able to say with pretty good certainty that that rock is older than F and M and R, right, and it's younger than I. If you knew the age of I was 300 million years ago, you could estimate how old B is, right? But really it's an estimation based on where the rock is found. Wouldn't I be bedrock? Yes, Sydney, it would. But thankfully, we don't have to know that. But I wanted a visual to show you guys that really it's based on where the rock is found. So if you have a rock that you find in your backyard on the ground, can you use relative dating to figure out how old it is? Sydney says yes. How? Well, where you find it, yeah, but you're going to find it on the top. So does that tell you anything? It tells you that it's the newest rock, but does it tell you how old it is? No, right? So in that case, it wouldn't be really helpful. Yeah, you could say it's young, it's new rock, right? But you would need to know how old that rock is, right? Do we know? Do you know how many millions of years old the rock is that's outside? I don't, right? I'm sure that you could Google and figure that out. But we need to be able to compare to layers of the earth in order to figure that out. So you would need to dig like a humongous, 300-foot deep section and compare different layers of rock. Not easy to do, not recommending that you do that. But if you become any kind of geologist, right, you'll get to do stuff like that in the field, which is pretty fun. Okay, evolution of life, right? I know this was a really confusing lesson. Excuse me, because they wanted you to do that virtual tour, right? Which is a fancy way of saying PowerPoint. Really, the main thing that you should get from that lesson is fossils are a huge factor for supporting the theory of evolution, right? And they show how organisms have changed over time. So we think, well, basically we know that 95% of all species that have existed on Earth are now extinct. How do we know they existed? Well, we have fossils, right? Otherwise, we wouldn't know. You could easily say, oh yeah, look at this thing I drew. It once was an animal. Hey, it might have been, who knows? But unless you have a fossil, no one's believing you, right? So fossils are the evidence that shows us which organisms existed and how they've changed. So most of the species that you see today, right, haven't been around for millions of years, right? Some of them have been, like ferns, those really basic plants. those have been around forever, right? They survived millions of mass extinctions. Excuse me, millions of mass extinctions. They've survived mass extinctions and millions of years of change, right? So ferns, a nice simple plant, thriving, right? Other things like humans have not been around nearly as long as ferns. Ferns also have more chromosomes than you, right? They actually have more DNA than you, which is weird because they don't really use it. So yeah, ferns are useful. They're edible, right? They can do a bunch of other stuff. Oh yeah, ferns have 1,400 and something chromosomes, and you have 46. Yeah, ferns are killing it. So regardless, right, there are obviously organisms have changed over time because we can see how they've changed in fossils. If this is something that's interesting to you, I linked this video here, which maybe we'll watch if we have time at the end. But I want to make sure we get to the DBA. I can't see my time. There we go. Oh, we're only 30 minutes into this? We'll have time probably. But it's on the evolution of whales, right? And they actually talk about fossils. They talk about other evidence as well. But they found fossils of whales that had back legs, right? Which is pretty weird. And whales still have a hip bone in their bone structure, right? So bones are great for fossils, but we can also see other things like humans have an appendix, right? What does your appendix do? Does anybody know? Collects bad stuff? That's a good question. It pretty much does nothing. It has a mild role in immunity, but not really. Mostly what happens is it gets infected and kills you, right? And then, yeah, it bursts, right? And people end up having to have it taken out. Pretty common. My sister had to have hers out. So the appendix used to do something though, right? It's not just there for no reason. It used to actually help you digest fiber. So right now, if you eat fiber, right, like plants, whatever, it makes you poop, right? People eat fiber to help them poop. Before, you actually used to be able to break down that fiber and get nutrients from it. That was back in the good olden days when we basically were eating like leaves off the ground, right? Because there wasn't anything else. So now that we don't really need to do that because we're eating meat, right? We're eating beans and all these other things. We're not just eating straight up vegetables. We don't really need the appendix, and over hundreds of years, right? Thousands of years even, it's been phased out essentially. Scientists predict that in another maybe 2,000 years or so, it won't be there anymore, right? It'll actually just not exist. Now, that's cool, but again, could an appendix be fossilized? No, right? Because it's an organ, it doesn't have a bone. So that's something that we can only track because we now know sort of that it exists, and we can track back in time to other organisms and we can piece together the narrative. But otherwise, if it's not a bone, we wouldn't know. So we're not even seeing all the changes that have happened over time is what I'm trying to get at here. So I see people talking about cloning. Trying to clone a woolly mammoth. Yeah, it is cool. Yeah, I mean, cloning has been moderately successful, but usually the organism dies pretty young. I mean, come on, Dolly the sheep. Yeah. If you consent to being cloned, I don't think they're attempting to clone humans yet. But I don't know. I would say probably go to Russia or China if you want to get cloned. They'll be the first to do it, not here. Okay, DBA. DBA time. So if you haven't done a DBA in the Google Doc before, it's pretty easy. Here's a link to the Google Doc. We do have 16 people, so the Google Doc might have a mild heart attack, but we'll see. What you're going to do is, Alina's doing a great job modeling for us right now. You're going to pop your name into one of the boxes, and then I wrote the questions here. That way you can kind of take your time with them, right? And we're going to kind of go over them a little bit, and then I will let you keep writing in the document, and then I'm going to input grades based on the document. So the first question is If a fossil is brought into the lab and the scientists did not note which layer of rock it was found in, can we use relative dating to determine age? Why or why not? You can't exit the meeting. Oh, Ian, go to the top of your screen and click exit full screen. See if that works for you. Otherwise, when the meeting ends, you can do it, right? Because I'm gonna wait a few minutes before I input grades. Yeah, if your internet's being slow, Sydney, that's fine. Just think about what you're gonna write, right? And you can always write it again once the Google Doc kind of chills. So you're deciding if a scientist finds a rock, but they don't know what layer of rock it was found in, can we use relative dating? Second question is, why is the geologic scale broken into periods? Something that we discussed in the beginning. A couple great answers from people there already that you could easily put into your own words. And the third question is, what is one organism that has lived on Earth but is now extinct? And how do we know? That one, you might know one already because there's a pretty obvious one. If you want to be unique, you might even research for that question. All right, let's see. We got a lot of answers. Yes, we can. The relative dating because it determines the life of the rock. Are you sure? Does relative dating tell us anything if we don't know where the rock was found? I see a lot of yeses. We can because you can use the sample material because it's an estimate. It is an estimate, but what if we don't know anything else about the rock? So I see a lot of you guys saying, well, yeah, we can use absolute dating. Well, we could, yeah, but I'm not asking about absolute dating. I'm asking about relative dating. Can we use relative dating to determine a rock that someone brings in and doesn't tell us where it's from? Excellent response to what I just said. Ian's changing his answer to no. There's not enough information. Exactly. You can't, right? Unless that person tells you what layer of rock it was found in or where it was found, you're going to have no idea what the age is unless you do absolute dating, right? Of course, if you brought it to a lab, they would do absolute dating, right? But I'm saying, can we do relative dating? Remember, relative means a guess based on where the rock is found in those layers. On the module or on the Google Doc, Travis? Okay, on the Google Docs. Okay, so Travis, you can either type your answers in the chat and I'll paste them in for you, or you can just wait until a lot of people have left the Google Doc because then it'll probably let you get in there. Because it might be just overwhelmed right now with the amount of people typing on it. Yeah, same thing. If you're having issues on it, that's fine. Just be thinking right now, listening to what I'm saying, right? You could even jot your answer on paper and you can always add it in once your internet relaxes, which it will once everyone gets out of the doc, right? Because it's a lot. We have 16 people in a doc at once, which I don't think Google had in mind when they created Google Docs, but too bad. Okay, so good. I see a lot of good edits to question 1. Question 2, why is the geologic scale broken into periods? Because we see evolution, essentially. Alina, that's a good point, right? We can see how organisms have changed over time and group them together. Let's see. To make it easier to classify and organize fossils. Excellent answer by Dylan. So it's easier to find the sections, right? Their time periods. Exactly, right? Just like how we break up minutes into seconds kind of stuff. Smaller periods, etc. Okay, there's sections and time periods, so everything isn't jumbled up. We can differentiate. It's easier to sort significant events. Good. Yeah, so it could be organized, otherwise it would be confusing. You're right. If we just talked in millions of years ago, it would be super confusing when we were talking about. And Samantha, thank you. I see your first question. I'm going to try to paste it in here for you. Okay, I see the dodo bird as a species that is extinct. Good. How do we know that it existed, though? Saber-toothed tigers. There's only fossils of them. Excellent answer there, right? Fossils is excellent proof. A kiwi. It's been proven that they're extinct. How has it been proven? Dinosaurs, yeah, that was the obvious one, right? Was the dinosaurs. The trilobites have evolved into something else, right? So they no longer exist, but their relatives exist. There's a lot of organisms. Okay, good start, Alina. Now give me a specific example. Dinosaurs, right? Would be a good example. Woolly mammoth, it's a good one. T-Rex, oh yeah, thankfully no longer around. Although I don't know, it seems that Haley is sad that the dinosaurs aren't around anymore. We'll put you in Jurassic Park 5, Haley, okay? How's that? Oh, also, side note to Haley and Sydney, because I know you guys were on the field trip, there's a picture of me where it looks like I'm making the cactus hand symbol, but I really wasn't. I was just like talking. It's on the Miwa Facebook. It's pretty entertaining. All right, Samantha, I got your second question. Okay, this is looking good, guys. Nice job on these questions. The first one I think was the hardest because I was kind of tricking you there by mentioning relatively. We know this because there are bones and fossils. Perfect. That's evidence, right? We can also get DNA evidence in some cases, depending on how old the fossils are, which is pretty cool. Let's see. Saber-toothed tigers, trauma. Okay. All right. So that pretty much concludes today's virtual session. I'm going to put the link to this whale video for if you'd like to watch it. It's 11 minutes long. It's pretty interesting.
So instead, we'll focus most of our attention.
Okay, guy. That's the guy's voice. So if that's something that you're interested in watching, right, obviously not required. It is something that I make people watch in biology, though, because it's a really good summary of different types of evidence for evolution. But they do talk about fossils, and it is pretty interesting how many fossils they have that are related to whales, right? I didn't know there were so many whale fossils. So if you want to watch that video, go ahead and check it out. Otherwise, finish up your answers in the Google Doc. I'm going to be putting answers in for that DBA later in the afternoon. Is there a code? No, there's actually not, Vitaly, because you being here in the Google Doc is how I'm going to keep track of you coming to the session today. Great question. Okay. So does anybody have a question about anything that we've done? I know a few people were having a hard time in the document. You can always wait a little bit and try again. And if you're still having issues, then send me an email. Okay. Awesome job, guys. So I'm going to end the session, and I will be posting, oh, Samantha's third answer here. I will be posting the recording just in case you want to go back if you missed the beginning or something like that. Otherwise, does this count as an assignment? Yes, Dylan, this counts as your discussion-based assessment. So, oh, good point here by Autumn. Do you need to copy the link and turn it in? You can. The thing is, I'm going to put a grade in for you. It's not going to disappear off your calendar. So you might want to post the link to the Google Doc as your DBA. And Dylan, you'll see it's assignment like 5.05 or something like that. It's called DBA. It's a discussion-based assessment. That's what we just did in the Google Doc. So yes, this does count as an assignment, right? So yeah, you might want to, you can even say something like, I was in the virtual session, right? Because I'm going to use the document to put in whoever did it. So if you care about it going off your to-do list, then turn something in. If you don't, I'm going to put the grade in, and the grade's going to count without you turning something in. So hopefully that answers your question. Okay, otherwise that's it, guys. I will see you next Friday at 12.